In today's session we will be discussing about some example problems and questions related to the topics that we have learned so far, and these topics are mainly associated with properties of pure substances and concept of heat and work. So, before starting with any problem, let me start with a simple school level question. Let me ask you a question. Let us say that there is some ice which is heated at a constant pressure. What will happen to the ice? So, this appears to be a very naive question, you know, that there is ice, it is heated at a constant pressure. So, normal intuition, a junior school child will say that if the ice is heated, it will get converted into water, liquid water, and then eventually water vapor. The answer of this question is not so simple. It is not complex either, but it is not that obvious, and to give an answer to this question, it is important to draw the phase diagram of water. So, if you look at this diagram, there are certain lines which I will explain. So, this is solid, this is liquid, and this is vapor. So, the saturation process, the liquid vapor phase transition, is this process which we have earlier described through the saturation pressure versus saturation temperature diagram. Now, you can see in this diagram that there is a very interesting point, state point, which is called as triple point. This is the point where the solid, liquid and vapor, they all coexist. So, for water, this triple point data corresponds to 0.6113 kilopascal and 0.01 degree centigrade. Okay. So, if you are there in the solid region, what will happen if you heat it at constant pressure? That is, if you follow a horizontal line, it depends on whether you are here or here or maybe here. So, if you are here, that is, if your pressure is greater than the triple point pressure, then the solid ice will get first converted to liquid water and then eventually to water vapor. So, this process is called as melting and this is called as vaporization. On the other hand, if you are below this triple point pressure, then if you heat the solid ice at constant pressure, it will get directly converted into vapor without going through the intermediate liquid step. This is known as sublimation. On the other hand, it is possible that if you heat it at the triple point pressure, then the solid ice will eventually pass through a combination of states where all the three phases, solid, liquid and vapor, can coexist. So, it will pass through the triple point. So, on heating the solid ice, what will happen at a constant pressure? It depends on where you are located in this phase diagram, and therefore this needs to be understood very carefully. Okay. So, with this little bit of short question, let us get into our tutorial problems. So, the next problem that we will discuss, please look into this. This is problem number 1.4. So, this problem number 1.4, this is from the chapter of properties of pure substances. This problem says, this problem describes that a steel tank containing 6 kg of propane at 20 degree centigrade with a volume of 0.015 meter cube. The tank is now slowly heated. Will the liquid level rise or eventually drop? What happens if the initial mass is 1 kg instead of 6 kg? So, again what is our intuition? So, the physical problem is there is a steel tank in which there is propane. So, now if we heat it, what is the general intuition? The general intuition is the liquid level will go down and it will, the vapor zone will be more. Let us see whether this answer is correct or not. So, to understand this, let us draw the phase diagram of propane. So, in this phase diagram, so let us say it is TV diagram. Let us identify what is the critical point. So, this data is given for this problem. So, the critical point for propane, it is given as critical point specific volume 0.004604 meter cube per kg. So, this is given. Now, I will tell you that how to solve this problem. Instead of getting into numbers, you have to figure out whether your initial volume, specific volume given is in this side or in this side of the critical point data. See, this tank is rigid, that means the when you are heating it, what is happening? How do you show it in a TV diagram? If you are heating it, see, because the total volume is constant and the mass is constant, volume per unit mass or specific volume is constant. So, at constant specific volume, because of heating, the temperature is increasing. So, it could be either this or this, depending on what is the initial volume. If it happens like this, so what will happen? See, here the quality value, the x is very small, almost close to 0, and then once it is heated, the x value is increasing. So, this is the situation where you have the quality increasing. Okay. So, when the liquid, when the quality is increasing, what will happen here? So, let us see. So, it is better not to say quality increasing, but it is the other way. So, this is the case where it is quality increasing. So, this is approaching saturated liquid. It is quality decreasing, not increasing. By mistake I told quality increasing. So, this is what it is approaching saturated vapor. Why? Because this is the saturated liquid line and this is the saturated vapor line. So, now let us look into the problem data. Your specific volume at state 1, which is given V1 is 0.0025 meter cube per kg. This is less than V critical. So, if you heat it, then it is approaching the saturated liquid line. That means actually the liquid level is rising. On the other hand, in the next case, it is given that what happens if the initial mass is 1 kg. So, this is 1 prime. So, V1 prime. So, if you calculate it, this is 0.015 meter cube per kg. How will you calculate it? Its volume at this state divided by the mass. So, this is greater than V critical. So, this means liquid level will fall. This means liquid level will rise. So, the moral of the story is whether liquid level will rise or fall will depend on what? Whether liquid level will rise or fall will depend on whether the initial state is in the left of the critical point or in the right of the critical point. If it is in the left, on heating it will approach the saturated liquid line. So, the liquid level will rise. If it is in the right, then on heating it will approach the saturated vapor line. So, the liquid level will fall and vapor will increase. Okay. So, this problem again gives us a clue that on heating of a liquid, it is not necessary that liquid level will fall. The liquid level may rise or fall depending upon the situation. Let us get into the next problem. This is problem number 1.5. This is actually the last tutorial problem of chapter 1, that is properties of pure substances. So, it says that there is a piston cylinder arrangement loaded with a linear spring and an outside atmosphere. Let me draw this schematically in the board. So, in this case it contains water at 5 MPa 400 degree centigrade. State 1. So, system is water. State 1 5 MPa 400 degree centigrade. Normally when pressure and temperature are both given, you must understand that it is either superheated vapor or subcooled liquid. So, this is not too high a pressure, that means this state is expected to be in the superheated vapor region, you can look into the table of superheated vapors to calculate its specific volume. So, if you see what is the specific volume corresponding to it, this is 0.05781 meter cube per kg. This you get from the table. I am just giving you the data so that once you look into the table you can check whether you are getting this value or not. If the piston is at the bottom, the spring exerts a force. If the piston is at the bottom, means if the volume is 0, if V is equal to 0, this is a hypothetical state, then P lift is equal to 200 kilopascal, that is the spring force, and the spring is a linear spring, that means the force is proportional to displacement, that means the pressure is proportional to the volume for the spring. The system cools from state 1 until the pressure reaches 1200 kilopascal. So, if you draw the PV diagram, so how do you know what is the PV, how the PV diagram looks? See, you have the state 1 and there is another point which will be lying on the PV characteristics of the system. Because of the linearity of the spring, the pressure versus volume will be linear. So, you can expect, so this P is P lift. So, what we can say is that the state point 2 will be somewhere on this line. So, for state point 2 you know what is the pressure. What is the pressure? The pressure is 1200 kilopascal. So, question is what is V2? Let us say, let us suppose that the state point 2 is here. So, we can write the equation of the line as, remember the equation of the straight line is y minus y1 by y2 minus y1 is equal to x minus x1 divided by x2 minus x1. So, here y is like P and x is like V. So, P minus P1, P minus P lift by P1 minus P lift is equal to V minus V lift is 0 divided by V1 minus V lift. Now, this equation will be satisfied by the data point 2. So, you substitute P equal to P2, you will get V equal to V2. So, from this equation you can find out what is V2. So, if you find out what is V2, this is 0.01204 meter cube per kg. This V2 is less than Vg at P2, but it is greater than Vf at P2. So, that means at P2 this is Vg and this is Vf. So, it is between Vf and Vg, that means it is in the two phase region. So, the problem is, so we have identified all the state points. So, our process is something like this. Now, let us look into the problem. You find out the final state and plot the process in the PV diagram. So, also find the initial mass. So, how do you get what is the initial mass? So, you have a volume that is given 1 meter cube, sorry 0.1 meter cube, not 1 meter cube, 0.1 meter cube. So, what is, so specific volume is volume per unit mass. So, from here you can get the mass of the system. Although the volume changes, the specific volume also changes, it adjusts itself in such a way that the mass of water within this remains the same. This is a control mass system, for example. So, the final state is, this is the process in the PV diagram, and the final state, the pressure is the final, what is the temperature at state 2? From the steam table you should see what is the saturation temperature corresponding to 1200 kilopascal, that is the temperature at state 2. The answer to this state 2 is 188 degree centigrade and the mass is 1.73 kg. So, M is 1.73 kg, T2 is 188 degree centigrade and V2 is 0.01204 meter cube per kg. This is the answer to this problem. Okay. Next, let us work out another problem, this time from chapter 2, that is heat and work. So, from chapter 2 we have already worked out the problem 2.1. So, let us work out another problem. Let us work out problem 2.3. So, I am projecting the problem 2.3 in the screen so that you can have a look into it. So, very similar to the previous problem, 2 kg of water is contained in the piston cylinder arrangement with a massless piston loaded with a linear spring and outside atmosphere. Initially the spring force is 0 and P1 is equal to P0 is equal to 100 kilopascal with a volume of 0.2 meter cube. If the piston just hits the upper stops, the volume is 0.8 meter cube and temperature is 600 degrees centigrade. Heat is now added until the pressure reaches 1.2 megapascal. Find the final temperature, show the PV diagram and find the work done during the process. So, let us try to make a sketch of this. See, for initial problems I have shown some detailed calculations, but as we proceed further and further I will tell you, give you the clues of how to solve the problem. In that way, within a limited time we can discuss more problems instead of getting into the detailed calculation of individual problems. So, this is the schematic of the problem. This is the spring, again a linear spring. This is water. These are the stops. So, the state, this is our system. So, whatever by dotted line we are presenting is the system boundary. So, state 1, you know what is specific volume at state 1, this is 0.1 meter cube per kg. So, how do you know this? You have the mass of the total system as 2 kg and the volume is 0.2 meter cube. So, this is volume per unit mass. At state 2 which is the stops V2 is equal to 0.4 meter cube per kg, because it is given that the final volume at the stops is 0.8 meter cube and that divided by 2 kg is 0.4 meter cube per kg. Also T2 is given, T2 is 600 degree centigrade. So this combination will give you what is P2. From table of water, of course. Now you can see that the final pressure which is given, let us say that is state 3, is 1.2 MPa. This is greater than P2. Therefore, what will be the physical process? On heating, the piston will move up, it will reach the stops, and slowly when it moves up and it reaches the stops, after that the pressure will build up inside at constant volume from 1 MPa to 1.2 MPa. So if you draw the PV diagram for the process, so you have from state 1 to state 2, and state 2 is in the superheated vapor region, so it will be here, and then from state 2 to state 3, a vertical line. You can plot all the relevant data like P1, P2 and P3 in this diagram. So we have plotted the PV diagram for this. This again, this is a straight line because it is a linear spring. The force is proportional to the displacement, that means pressure is proportional to the volume. So the question is, find the final temperature. How will you know state 3? So state 3 is, this is P3 and V3 is equal to V2. This will identify what is state 3 and then that means what is T3. This is 770 degrees centigrade, that is the answer to this. What is the work done? The work done is simply the area under the PV diagram. So this is the work done. So W12 is half into P1 plus P2 into V2 minus V1. This is basically integral PdV. So this is 330 kilojoule. That is the answer to this problem. Let us work out the next problem. So this problem was 2.3. Next we will work out the problem number 2.5. I am trying to work out as many number of problems as possible so that you gain an insight into problem solving. And remember that problem solving is a very important skill in thermodynamics, and as I told you, one of the important challenges in thermodynamics is that each problem has a unique way of addressing and it is very difficult to cast a formula for that. So next problem 2.5. The problem is projected here. Two springs with the same spring constant are installed in a massless piston cylinder arrangement with the outside air at 100 kilopascal. If the piston is at the bottom, both the springs are relaxed and the second spring comes in contact with the piston at V equal to 2 meter cube. The cylinder initially contains ammonia at -2 degree centigrade with quality equal to 0.13 and volume as 1 meter cube, which is then heated until the pressure reaches 1200 kilopascal. At what pressure will the piston touch the second spring? Find the final temperature and the total work done by ammonia. So, this is a very interesting problem. So, here there are two springs. So, let us look into the problem data. The initial volume is 1 meter cube. So, let us say V1 is 1 meter cube, and then you have at state 2 the volume is 2 meter cube. State 2 is the situation when the second spring comes in contact with the piston. So, after this both the springs are in contact with the piston. So, because the spring is linear up to 1, between 1 to, there will be the pressure versus volume variation will be a straight line. Okay. So, if it is a straight line, then what will be the straight line, what will be the equation of the straight line? It is given that when the volume is 0, you have P0 is 100 kilopascal. Okay. And what is the pressure at state 1? How do you know? So, state 1 you have this system is ammonia. So, you have to look into the table of ammonia, not water. So, ammonia minus 2 degree centigrade, quality equal to 0.13, that means it is in the saturated state of the two phase region. So, P1 is equal to P sat of ammonia at minus 2 degree centigrade. So, ammonia is a very good refrigerant. So, it is used as a refrigerant, and normally this is such a data that it is being talked about. So, this, if you look into the table of ammonia, this is 396.775 kilopascal. So, you know P1 V1. Now, how do you know where will be state 2? You simply join these two by a straight line and extrapolate it, because it is a linear spring. So, wherever it will cut this line, that will be your state 2. So, again you can identify state 2 by noting that P2 minus P0 by P1 minus P0 is equal to V2 minus V0 by V1 minus V0. So, from here you can say what is P2. At this stage the second spring comes in contact. So, P2 is 694.875 kilopascal. At this stage the second spring comes in contact with the first spring, with the piston. So, that means both the springs are now in contact and both springs have same stiffness. Remember, the slope of the PV diagram represents qualitatively the stiffness. If it was a force versus displacement diagram F versus x, then the slope actually represents stiffness. Pressure is force per unit area and volume is the displacement times the cross sectional area of the cylinder. Therefore, this slope does not quantitatively represent stiffness, but it qualitatively represents stiffness. So, if there are two springs now coming together, the stiffness will be doubled, and when the stiffness will be doubled, then what will happen is that from 2 onwards you will get a variation of this slope is 2 into slope of the line 0, 1, 2. So, that is how you can fix up the straight line, and once you fix up the straight line, how do you know what is the final state? The final pressure is 1200 kilopascal. So, when this is 1200 kilopascal, state 3, then this is the corresponding V3. So, from the equation of the straight line you can get what is V3, and then the work done is so if you know what is this pressure and what is the total volume, you divide the total volume by mass, so you get specific volume. So, state 3 is governed by P3 is equal to 1200 kilopascal and V3 is known. So, that will give you what is T3, which is 51 degree centigrade. From ammonia table is 51 degree centigrade. And what is the work done? The work done is, so 1 to 2, so 0 to 1 is not the actual state, it is the hypothetical situation given just to know the equation of the straight line. So, better it is shown by some dot. So, the actual physical process is from 1 to 3. So, 1 to 2 and then 2 to 3. So, this shaded work, the work done is the shaded area, and this comes out to be 1342.6 kilojoule. Okay. So, let us work out another problem quickly before we conclude this tutorial session on the first two chapters. So, the next problem is problem 2.6. There is a cylinder with a cross sectional area of 7.012 centimeter square. This has two pistons. If you look into the figure you will understand it very clearly. The upper one has mass of 100 kg, is initially resting on the stops. The lower piston is almost massless, so it is mass is having 0 kg, has 2 kg of water below it with a spring in vacuum. So, between the two pistons there is vacuum, so there is no atmosphere. The spring in vacuum connecting the two pistons. The spring force is 0 when the lower piston stands at the bottom, and when the lower piston hits the stops the volume is 0.3 meter cube. The water initially at 500 kilopascal and 0.00206 meter cube is heated to saturated vapor. You have to find out the initial temperature and pressure that will lift the upper piston, the final temperature, pressure, volume and the work done by water. So, this is again is a very interesting problem, and so let me try to draw a schematic of this. So, in this situation, so there is a situation, first what will happen, first the bottom piston will be lifted. After some time there will be a situation when both the pistons move together. So, what is that pressure when both the pistons move together? So, to understand that, we draw the free body diagram of the system when both the pistons are connected. So, this is piston 1, this is piston 2. Okay. So, here there is no atmosphere, here there is vacuum, on the top there is atmosphere. So, P0 into A inside the pressure is, let us say, P lift, and you have the weight of the piston. So, MP1 into G, this is MP2 into G. One of the pistons is given of negligible mass, but I am solving the general problem no matter whatever is the mass given. So, under mechanical equilibrium all forces are balanced. So, P lift into A is equal to P0 into A plus MP1 plus MP2 into G. So, P lift is equal to P0 plus MP1 plus MP2 into G by A. So, if you plug in all the values, this will come out to be 1500 kilopascal. Okay. So, now let us try to draw a PV diagram to visualize the process. So, this is water. This problem deals with properties of water. So, let me draw the phase diagram, which is the situation for water. So, when the bottom piston is only moving, how will the pressure versus volume diagram look like? When the bottom piston is only moving, the top piston is against the stops. So, the force versus displacement will be based on the linearity of the spring. So, the spring will be compressed as this piston is going up and the pressure will increase linearly with the volume. What will be the equation of the straight line? For that, one important data point is given, that the lower piston has mass 2 kg and with a spring in vacuum to connect the two pistons. So, if the volume is 0, the pressure is also 0. Why? When the volume is tending to 0, at that point what is exerting pressure from the top? What is exerting pressure from the top is this atmosphere, which is 0, and then the weight of this piston, which is also 0, MP2 is 0. Therefore, if the volume is 0, the pressure is 0. This is a very important data point for the problem. Then it is given that there is a state 1, P1 and V1 are given. So, state 1, V1 is 0.00103 meter cube per kg, P1 is equal to 50 kilopascal. So, this is state 1 somewhere. I am not checking whether it is in the two phase or in the compressed liquid region. So, I am just hypothetically showing it. It is your duty to see whether state 1 is in the two phase or in the compressed liquid region, and accordingly you have to plot it properly. Then see, the state 0 is hypothetical state, but from 1 it is the real situation that is coming into the picture as the process starts. From 1 it goes up to a state which is, let us say, 1A, where the pressure is given. So, the pressure at state 1A is this P lift, this is 1500 kilopascal. So, let us say this is 1A. So, this is 1500 kilopascal. After this, the PV diagram will be horizontal, because the spring force will not be coming into the picture, because the action reaction force, they are nullified within the system. So, it is a constant pressure process after that. So, the constant pressure process from 1 to here, it will be a constant pressure process. The water initially is at the state 1, now is heated to saturated vapor. Question is, what is the volume of the stops, the volume at the stops? So, if you calculate the volume at the stops, so this is 0.3 by 2 is equal to 0.15 meter cube per kg. How do you get this? See, it is given that when the lower piston hit the stops, the volume is 0.3 meter cube. So, the specific volume is 0.2 by this. Now, this, if you look into the table, is greater than Vg at 1500 kilopascal. This means that before hitting the stops, this reaches the saturated vapor, and then the process ends, because it is given that the water is heated to saturated vapor. So, the PV diagram for this particular case is this one. Now, if what would have happened if V stop is less than Vg at 1500 kilopascal, then it would have stopped somewhere here, and then the process would have been a vertical line till the saturated vapor is reached. So, that is why I tell that thermodynamics is such a subject where through formula based learning you cannot follow the subject. What you should do is, you should interpret the situation based on the data. So, here because Vg at 1500 kilopascal is less than V stops, so the process ends at saturated vapor here. However, if V stop was less than this Vg, then it would have not been able to go up to this, it would have stopped somewhere here, and then it would have been a vertical line, so that at constant volume the saturated vapor state is reached. So, for this particular data given, this is the PV diagram what I have shown by this line, and then the answers to this problem, initial temperature is from this state, it is T1 is 81.33 degrees centigrade. Then the P lift is 1500 kilopascal, that is already told, and then what is the final specific volume is 0.15 meter cube per kg, and the work done is the area under this PV diagram. Shaded area, this is 348.91 kilojoule, that is the answer to this problem. So, again I am telling you that for working out these types of problems, it is always useful to visualize the process by drawing the PV diagram, because the process diagram is not given in form of equation. You have to visualize it through the physical process and then find out the work by constructing the area under the PV diagram. Okay, thank you very much for your attention to this tutorial session where I tried to work out a few problems, and we will start with the first law of thermodynamics in the next session. Thank you very much.